Welcome to Precalculus Concept 37B, Vectors Part 2 of 2, and there's only 3 boxes. So let's get into this right away here. Number 1 is an example. We're going to sketch the vector negative 3i plus 2j and then find its magnitude. In the last video, I told you that a vector can be broken down into its component form. So the negative 3i just means that it has to be 3 units in the I direction, and the 2j means it needs to be 2 units in the j direction. So if I started at the origin, for example, negative 3i plus 2j could be represented like this. This would be negative 3i in that direction, and then the 2j in that direction. And we want to find its magnitude. So basically, we want to know how long is this thing. So I'm looking for the magnitude of vector v. So we learned in the last video that the magnitude is represented by 2 bars on either side, and it is the square root of negative 3 quantity squared plus 2 quantity squared, since it's just the I and the j components. This goes straight from the Pythagorean theorem. So this is going to give me the square root of 9 and 4. This is going to give me the square root of 13, and I can leave it just like that. So its magnitude is worth the square root of 13. It is to note that it doesn't matter where I put this in the plane. Right, if I move this whole thing around anywhere in the plane, like if I drew my vector over here, right, the magnitude would still be a value of the square root of 13. So it doesn't really matter where you put it, because you are allowed to move vectors in the plane assuming you don't change their direction or their magnitude. Okay, box 2 is another example of the same concept, just presented in a different way. Let's say that vector v has an initial point at 5, 2. So I'll do that for you. I'll go 5, 2. And let's say it has a terminal point at negative 3, negative 4. So I'll go negative 3, negative 4. So this is it. So this is my initial point, and this is my terminal point. So I can mark that with an I and a T if I wanted to remind myself of which way it was going. And this is called vector v. So it just says write the vector in terms of its I and j components. Okay, well, I is the horizontal component. So if I just count 1, 2, 3, 4, 5, 6, 7, 8. So this would be negative 8i. And then j components would be 1, 2, 3, 4, 5, 6, negative 6, j. So I could represent this vector v, could be represented as negative 8i minus 6j. And that's all we're looking for that problem there. Okay, last box, number 3, is an example. It says if we know that vector a is represented by its vector components of 3i plus 4j, and vector b is represented by its components negative 7i minus 3j, then we can find the following here. So what if I'm interested in 3 times the vector a? So I'm going to do 3 times vector a is going to be 3 times the vector components of 3i plus a 4j. So that's just going to be 3 times your 3i plus 3 times your 4j. So that's going to give you 9i plus 12j, and it really is that simple. That's all we're trying to do, is we're just trying to increase that vector's magnitude 3 times. That's a scalar. What if I wanted to add these 2 vectors together? What if I wanted to take 3i plus 4j, and I want to add that to negative 7i minus 3j? Well, you do exactly what you would guess you would do. You add the like components. So if I take 3i and I subtract 7i, I'd get negative 4i. And then if I took a positive 4j and I subtracted a negative 3j, I would get a positive 1j. So that would be the resultant of a plus b. Similarly, if I wanted to do b minus a, I would just write down vector b's components of negative 7i minus 3j. And I would subtract off 3i, plus 4j. And remember to distribute that minus sign. So I'd have negative 7i minus 3j minus 3i minus 4j. And I would just add the like components. So negative 7 and a negative 3 is a negative 10i. And then a negative 3j and a negative 4j is a negative 7j. So I would like their components just like that. And if I had to graph these 2 things, well, I could easily graph them too, just by moving the vectors around from tip to tail.